Calculating reaction rates. The rate of a reaction tells you how much product forms or how much reactant is used up over a specific period of time. You calculate it using a simple formula. Rate equals the amount of reactant used or product formed divided by time. On a graph, the rate at any specific point is found by calculating the gradient of a tangent down to the curve. A steeper slope indicates a faster rate. As the reactants get used up, the reaction slows down, causing the curve to flatten out over time. In the exam, if they give you a curve on a graph, always draw a clear straight tangent line against the curve and calculate its gradient, which is change in y divided by change in x. Remember to show your working and state your units, which are usually centimeters cubed per second for gases or grams per second for mass. Remember, rate is just speed. A steeper slope means a faster reaction. Chemical reactions can only happen when reacting particles collide with each other with enough energy. This minimum amount of energy required for a reaction to take place is called the activation energy. If particles collide with less energy than this, they simply bounce off one another unchanged. Therefore, to speed up a reaction, you must increase the frequency of successful collisions. In the exam, when you're asked to explain why a factor speeds up a reaction, always phrase your answer using collision theory. State that the factor increases the frequency of collisions, which leads to a greater number of successful collisions per second. So what are the factors affecting rate? There are four main factors that speed up a chemical reaction. Increasing the temperature gives particles more kinetic energy, making them move faster. This means they collide more frequently, and a higher proportion of those collisions have enough energy greater than the activation energy. Increasing the concentration of a solution, or the pressure of a gas, means there are more particles packed into the same volume, which increases the frequency of collisions. For solids, breaking them up increases the surface area, exposing more particles to react at once. Adding a catalyst changes the reaction route entirely. Catalysts and activation energy. A catalyst is a substance that speeds up the rate of a chemical reaction but remains chemically unchanged at the end, meaning it's not used up. It works by providing an alternative reaction pathway that has a lower activation energy. This allows a much higher proportion of the colliding particles to have enough energy to react successfully. Because the catalyst is not used up in the process, you only need a small amount of it, and it can be used over and over again. Required practical, rates of reaction. The classic rates required practical involves reacting sodium thiosulfate with hydrochloric acid. As these two clear solutions react, they produce a fine yellow precipitate of sulfur, which gradually turns the solution cloudy. To measure the rate, you place the reaction flask over a piece of paper marked with a black cross and time how long it takes for the cross to completely disappear. A shorter time means a faster reaction rate. You repeat this process while changing the concentration of the sodium thiosulfate to investigate its effect. In the exam, you're often asked to identify the variables in this experiment. The independent variable is what you deliberately change. That's the concentration of sodium thiosulfate. The dependent variable is what you measure, which is the time taken for the cross to disappear. The control variables that you must keep constant include the total volume of the liquid, the temperature, and the depth of the liquid. Reversible reactions. Some chemical reactions can go both ways. A reversible reaction is always represented in a chemical equation by a double-headed arrow. In the forward direction, reactants turn into products. In the reverse direction, those products break back down into the original reactants. A classic example is ammonium chloride. Heating it causes it to decompose into ammonia and hydrogen chloride gases, but cooling those gases back down causes them to recombine into solid ammonium chloride. In the exam, always look out for the double arrow symbol. Remember that energy changes are also perfectly reversible. If a reaction is exothermic in the forward direction, it will be endothermic in the reverse direction by the exact same amount of energy. Dynamic equilibrium. When a reversible reaction happens inside a closed system, where no reactants or products can escape, it eventually reaches a state called dynamic equilibrium. This doesn't mean the chemical reaction has stopped. Instead, it means the forward and reverse reactions are occurring at the exact same rate. Because these two speeds are perfectly balanced, the overall concentrations of all the reactants and products remain completely constant. In the exam, the absolute keyword here is dynamic. If an examiner asks you to define equilibrium, your answer must include two specific points. The rate of the forward reaction equals the rate of the reverse reaction, and the concentrations of reactants and products remain constant. Crude oil and hydrocarbons. Crude oil is a complex mixture of a vast number of compounds called hydrocarbons are molecules made of hydrogen and carbon atoms only. Crude oil was formed millions of years ago from the remains of ancient biomass, mainly plankton, that settled at the bottom of oceans, where it was buried under mud and subjected to intense heat and pressure over millions of years. It's a finite resource, meaning it's being consumed much faster than it can actually form, and it will eventually run out. In the exam, because crude oil is a mixture and not a pure substance, it does not have a single sharp boiling point. Instead, it boils gradually over a wide range of temperatures as the different chain lengths separate. So crude oil is just nature's massive collection of carbon chains all tangled up together. Alkanes. Alkanes are described as saturated hydrocarbons. The term saturated means that all the carbon atoms are joined together by single covalent bonds, meaning the molecule contains the maximum possible number of hydrogen atoms. The first four alkanes you need to know are methane, 1 carbon, ethane, 2 carbons, propane, 3 carbons, and butane, 4 carbons. They follow the general mathematical formula CnH2n plus 2. As the carbon chain gets longer, the boiling point increases. The liquid becomes thicker and more viscous. It becomes less flammable and it turns darker in colour. In the exam, you must memorize the names and formulae of the first four alkanes: methane, CH4, ethane, C2H6, propane, C3H8, and butane, C4H10. Be prepared to draw their displayed formulae showing every single atom and bond line clearly. Remember the acronym MEPB? Monsters eat pupils' brains. Methane, ethane, propane, butane. Properties and complete combustion. Short-chain hydrocarbons are highly useful because they ignite easily and flow smoothly compared to the thick, long-chain hydrocarbons. Fractional distillation. This is how we separate crude oil into its different sections. The crude oil is heated until it evaporates. Then it's fed into a tall tower called a fractionating column. The column is hot at the bottom and cool at the top. As the vapours rise, they cool down. The long-chain hydrocarbons have high boiling points, so they condense and are collected near the bottom. The short-chain hydrocarbons have low boiling points, so they rise higher up before condensing and are collected near the top. Each collected part is called a fraction, and each fraction contains molecules with a similar number of carbon atoms. In the exam, the key idea is that hydrocarbons are separated by their boiling points, and boiling point depends on the length of the carbon chain. Useful fractions include petrol, kerosene for jet fuel, diesel, and bitumen for road surfaces. When any hydrocarbon is burned with an abundant supply of oxygen, it undergoes complete combustion. The carbon and hydrogen are fully oxidized, meaning the only two products formed are carbon dioxide and water. However, if oxygen is limited, incomplete combustion occurs. This produces toxic carbon monoxide gas, along with unburnt carbon particles released as black soot. In the exam, carbon monoxide is dangerous because it's a toxic, colourless and odourless gas. It binds irreversibly to the hemoglobin in your red blood cells, preventing them from carrying oxygen around the body. Remember the standard word equation: hydrocarbon plus oxygen gives you carbon dioxide plus water. Cracking. Industrial oil refining produces too many long-chain hydrocarbons from crude oil, which are thick and not in high demand. Conversely, there's a massive shortage of short-chain hydrocarbons, like petrol, which are highly sought after. Cracking is a thermal decomposition process used to break these long, less useful molecules down into smaller, more valuable ones. There are two main types: catalytic cracking, which uses a hot catalyst at lower temperatures, and steam cracking, which mixes the hydrocarbons with steam at very high temperatures. Cracking always yields a shorter alkane and at least one alkene, which is a type of unsaturated hydrocarbon used to manufacture plastics and polymers. In the exam, always specify that cracking requires high heat and either a catalyst or high pressure. Importantly, always mention that the process creates alkenes, which are far more reactive than alkanes and turn bromine water from orange to colourless. So cracking simply cracks the long, useless carbon chains in half, much like snapping a long stick into smaller, more useful pieces. Pure substances and formulations. In chemistry, a pure substance consists of only a single element or a single compound that's not mixed with any other substance. Pure substances can be easily identified because they melt and boil at precise specific temperatures. In contrast, a mixture does not have a sharp melting point. It will melt or boil gradually over a wide range of temperatures. A formulation is a very specific type of mixture that's been carefully designed as a useful product. In a formulation, every single ingredient is measured out precisely to ensure the product has the exact properties required. Examples include paints, medicines, alloys, and fertilizers. In the exam, a pure substance melts and boils at one fixed temperature. A mixture melts and boils over a range. This is the simplest way to tell them apart from a data table. So a formulation is a recipe. Every ingredient is measured out on purpose to get the exact result that you want. Chromatography. Paper chromatography is a method used to separate a mixture of soluble coloured substances, such as the different dyes in an ink. You draw a starting line in pencil near the bottom of the paper, place a spot of the mixture on it, and dip the bottom of the paper into a solvent. The solvent travels up the paper, carrying the different substances with it. Substances that are more attracted to the solvent travel further up, while substances more attracted to the paper travel less far. So the mixture separates out into individual spots. In the exam, always draw the starting line in pencil, never pen. Pencil is insoluble, so it will not run up the paper and ruin the result. A pure substance produces only one single spot, whereas a mixture separates into two or more spots. RF values and required practical. Chromatography. Each substance can be identified by its RF value. The RF value is calculated using the formula RF equals the distance moved by the substance divided by the distance moved by the solvent. Because it's one distance divided by another, an RF value is always a number between 0 and 1, and it has no units. In the required practical, you separate the colours in food dyes or inks, measure both distances carefully with a ruler from the pencil line, and calculate the RF value for each spot. In the exam, always measure to the centre of each spot, and always measure both distances from the same pencil starting line. The same substance will always give the same RF value in the same solvent, which is how you identify it. Testing for gases. There are 4 common gas tests that you must know. To test for hydrogen, you hold a lit splint at the mouth of a test tube. Hydrogen burns with a squeaky pop. To test for oxygen, you place a glowing splint into the tube, and oxygen relights the glowing splint. To test for carbon dioxide, you bubble the gas through lime water. Carbon dioxide turns the lime water cloudy or milky. To test for chlorine, you hold damp blue litmus paper in the gas. Chlorine bleaches the litmus paper white. It might turn red first because chlorine is acidic. In the exam, learn these word for word, including the result. Squeaky pop for hydrogen, relights a glowing splint for oxygen, turns lime water cloudy for carbon dioxide, and bleaches damp litmus paper for chlorine. The early atmosphere. The Earth is around 4.6 billion years old, and for the first billion years it was extremely volcanically active. These volcanoes released huge amounts of gas, so scientists believe the early atmosphere was mostly carbon dioxide, with very little or no oxygen, rather like the atmospheres of Mars and Venus today. The volcanoes also released water vapour and small amounts of other gases like nitrogen, methane, and ammonia. As the Earth cooled, the water vapour condensed to form the oceans. In the exam, be careful with the wording. We can't be completely certain about the early atmosphere because it was so long ago and there's limited evidence. So scientists use theories and models. The 2 big points are mostly carbon dioxide and little to no oxygen. How the atmosphere changed. 2 main changes turned that early atmosphere into the one that we breathe today. First, oxygen increased. About 2.7 billion years ago, algae and then plants evolved and began photosynthesis, taking in carbon dioxide and releasing oxygen. Over billions of years, this slowly built up enough oxygen for animals to evolve. Second, carbon dioxide decreased. A lot of it dissolved into the newly formed oceans, where it formed carbonate sediments and rocks. Carbon was also locked away inside the bodies of plants and animals, which over millions of years became fossil fuels such as coal, oil, and gas. In the exam, link oxygen rising directly to photosynthesis by algae and plants. Link carbon dioxide falling to it dissolving in oceans, forming sedimentary rocks and being trapped in fossil fuels. Greenhouse gases and climate change. Some gases in the atmosphere are called greenhouse gases because they trap heat and keep the planet warm enough for life. The main ones are carbon dioxide, methane, and water vapour. They work by letting short wavelength energy from the sun pass through to warm the Earth. They also absorb the longer wavelength heat radiation that the Earth gives off and re-radiate some of it back down. Human activities are increasing the amounts of carbon dioxide from burning fossil fuels and deforestation, and methane from farming livestock and landfill sites. This extra greenhouse gas is causing global climate change. In the exam, the consequences to learn include rising global temperatures, melting ice caps and polar ice, rising sea levels and flooding, more extreme weather, and changes to the distribution of wildlife. Always link human activity to the increase in greenhouse gases. Think of it like the greenhouse gases are a duvet around the Earth, and a thicker duvet traps more heat. Carbon footprint. The carbon footprint is the total amount of greenhouse gases, so carbon dioxide and methane, given off over the full life cycle of a product, service, or event. To slow down climate change, we need to reduce these footprints. We can do this by using renewable energy sources instead of fossil fuels, by being more energy efficient, by capturing and storing carbon dioxide before it reaches the atmosphere, and through government actions like taxes or carbon caps on businesses. In the exam, you might be asked why it's difficult to reduce carbon footprints. Good reasons include the high cost, a lack of public willingness to change habits, incomplete scientific information, and the difficulty of making international agreements between countries. Atmospheric pollutants. Burning fuels releases several harmful pollutants into the air. Incomplete combustion produces carbon monoxide, which is a toxic, colourless, odourless gas, and soot, which we also call carbon particulates, which causes breathing problems and global dimming. Most fuels contain small amounts of sulphur, which burns to form sulphur dioxide. At the high temperatures inside engines, nitrogen and oxygen from the air react to form oxides of nitrogen. Both sulphur dioxide and oxides of nitrogen dissolve in clouds to cause acid rain, and both also cause respiratory problems in humans. In the exam, match each pollutant to its problem. Carbon monoxide is toxic, particulates cause global dimming and breathing problems, sulphur dioxide and oxides of nitrogen cause acid rain and respiratory issues. Using the Earth's resources. The Earth provides us with everything we need for warmth, shelter, food, and transport. These resources are split into two types. Finite resources, like fossil fuels and metal ores, are being used up far faster than they can be replaced, so they will eventually run out. Renewable resources, like timber and fresh water, can be replaced as quickly as we use them. Sustainable development means meeting the needs of people today without damaging the ability of future generations to meet their own needs. In the exam, chemistry helps sustainability in many ways, improving farming and agriculture and developing new materials, as well as finding ways to reuse and recycle limited resources. Know the difference between finite and renewable clearly. Potable water. Potable water means water that's safe to drink. Importantly, potable water is not the same as pure water because it still contains low levels of dissolved salts and some microbes. In the UK, we make potable water from fresh water by choosing a suitable source such as a reservoir, river, or aquifer, then passing it through filter beds to remove solids, and finally, sterilising it to kill microbes. Sterilising can be done with chlorine, ozone, or ultraviolet light. In very dry countries with little fresh water, seawater must be desalinated by distillation or reverse osmosis, but this uses large amounts of energy. In the exam, remember the two clear steps for fresh water: filtration to remove solids, then sterilization to kill microbes. Desalination is only used when there's not enough fresh water because it's expensive and energy hungry. Required practical analysis and purification of water. In this required practical, you analyze water samples and then purify one by distillation. First, you test the pH of each sample using a pH meter or universal indicator. Then you find out how much dissolved solid is present by evaporating a measured volume of the water and weighing what's left behind. Finally, you purify the water using distillation. You boil the water so it evaporates. Then you cool the steam so it condenses back into a separate clean container, leaving the dissolved solids behind. In the exam, remember that distillation works because the dissolved solids have very high boiling points, so they stay behind in the flask while the pure water evaporates and is collected. The distilled water should have a neutral pH of 7 and leave no solid when evaporated. Wastewater treatment. Large amounts of wastewater are produced by homes, sewage, agriculture, and industry, and this must be treated before it safely returns to the environment. The treatment happens in stages. First, screening removes large solids and grit. Next, sedimentation lets the waste settle in a large tank, separating into a liquid called effluent on top and a solid sludge at the bottom. The sludge is then broken down by anaerobic digestion, so that's without oxygen, which also produces useful biogas. The effluent is treated by aerobic biological treatment, where bacteria use oxygen to break down the remaining organic matter and harmful microbes. In the exam, learn the order: screening, then sedimentation, then anaerobic digestion of the sludge, and aerobic treatment of the effluent. Note that treating sewage needs less energy than desalinating seawater, which is a common comparison question. Life cycle assessments. A life cycle assessment, or LCA, is carried out to work out the total environmental impact of a product across its entire life. It looks at 4 main stages: getting the raw materials, manufacturing the product, using the product, and finally disposing of it at the end of its life. At each stage, the LCA considers things like the use of resources, the energy needed, and any pollutants released to the water, land, or air. In the exam, be ready to explain why LCAs are not fully objective. Measuring the effect of pollutants involves making value judgments, so the results can be biased. For example, a company might design an LCA to make its own product look better. Energy and material can be used fairly accurately, but the impact of pollution is harder to judge. Reduce, reuse, recycle. The simplest way to make resources last longer and reduce environmental damage is to use less of them in the first place. The 3 R's put this in order. Reducing means using smaller quantities of raw materials and energy. Reusing means using an item again for the same or a new purpose, like refilling a glass bottle. Recycling means processing used materials, such as melting down metals or glass, so that they can be used in new products. Recycling metals in particular saves a huge amount of energy and ore compared with extracting fresh metal from the ground. In the exam, the order of preference is reduce first, then reuse, then recycle. A strong point to make is that recycling uses much less energy and conserves limited resources compared with mining and extracting new raw materials.